This is Engineer Nasir from NC Engineering and Technology. Today we are going to discuss a very important topic in the field of HVAC system, that is the chill water distribution system. As it is a very huge subject, so we will study it in parts. Based on the application of chill water pumps, we can divide the whole chill water system into four types. Number 1, constant flow primary chill water system. Number 2, variable flow primary secondary chill water system. Number 3 is the variable flow primary secondary and tertiary chill water system. And number 4 is the latest one, that is variable flow primary chill water system. We will discuss all four types in detail one by one. Let us start from the first one, that is primary constant flow chill water system. A constant flow chill water system we can define as the simplest chill water distribution system, where a set of constant speed pumps distribute fixed quantity of water at all times and the temperature varies to meet the load. This system uses three-way control valves, 8 air handler, that is HUs or FCUs, that allows some water to bypass the cooling coil during the part load conditions. At low loads, the chill water flow through the cooling coil is restricted in response to the supply air temperature to the space, but the total quantity returned to the chiller remains the constant. There are three major components of the constant flow chill water system. Number 1 is the constant speed chill water pump, number 2 is the chiller, and number 3 is the air handler, that is HUs and FCUs. All these components are connected together by a loop of chill water piping. Air handling devices, that is HUs and FCUs, have a chill water line parallel to the piping that is connected to the HUs and FCU with the help of a three-way valve. And it is the main characteristic of this system that make it different from all other chill water distribution system. Let us take first case 1 at full load condition. As we know, all the equipments are designed at peak load condition. Let us assume our HU are designed at 200 GPM and a delta T temperature of 12 degree Fahrenheit. That is the inlet temperature 44 degree Fahrenheit and outlet temperature 56 degree Fahrenheit. It means at a flow of 200 GPM with the delta T of 12 degree Fahrenheit, our HU will work at 100% efficiency. As we know, our system is a constant flow chill water system, so we will select a constant speed chill water pump that will give us the constant flow of chill water throughout the whole circuit. In the same way, we have selected the chiller with a constant flow of chill water through it with a fixed outlet temperature of 44 degree Fahrenheit, having 100% efficiency at delta T 12 degree Fahrenheit. Here you can see a three-way valve connected with the bypass line across the HU. At full load condition, it will not allow any water to bypass the HU. So now we can summarize: in a constant flow chill water system, at full load condition, a constant flow of chill water, in our case it is 1200 GPM, will flow throughout the circuit with the maximum delta T temperature that will help to get us the 100% efficiency from all our equipment, that is chiller and HUs. So at full load condition, this system will give us 100% efficiency and it is the best suited system to be used. Now we'll study the case 2, that is at part load condition, and practically our system operates most of the time on the part load condition. Before starting the study of a constant flow chill water system at part load condition, we must understand the operation of a three-way valve, as the difference between full load condition and part load condition of the system depends only the operation of the three-way valve. Let us assume our room design temperature parameter as indoor at 74 degree Fahrenheit and outdoor at 100 degree Fahrenheit, having a delta T of 40 degree Fahrenheit. When the air conditioning system will start, the room temperature will be at maximum, that is 114 degree Fahrenheit, but the air conditioning system will running continuously. The temperature inside the room will fall down, and for our study let us assume the indoor temperature became 94 degree Fahrenheit, that is the load became 50% of the design load. This indoor temperature will be sensed by the thermometer and it will give the signal to the three-way valve, and the three-way valve, after getting the signal from the thermometer, it will restrict some of the chill water passing through the AHU. Now the sum of the chill water that is coming from the chiller at 44 degree Fahrenheit will pass through the AHU, and some part of it will bypass at the same temperature through the three-way valve. And after the three-way valve, the chill water will mix at two temperature that will come from the AHU. It will be at 56 degree Fahrenheit, and the chill water that is coming bypass, it will be remain at the same degree of 44 degree Fahrenheit, and it will generate a chill water return temperature at a different degree Fahrenheit than design. Using the linear relationship between the coil heat transfer and the chill water flow rate, at 50% room design condition, 50% of the chill water will be needed to flow through the AHU, and 50% of it should be bypassed using the three-way valve. In our condition, we have designed the AHU for 200 GPM at full load condition. So at 50% load, 100 GPM should pass through the AHU and 100 GPM should pass through the bypass using the three-way valve. After the three-way valve, when this 100 GPM at 56 degree Fahrenheit and 100 GPM at 44 degree Fahrenheit will mix, it will generate a temperature of 50 degree Fahrenheit for the chill water return. Practically, the coil characteristics are non-linear, and for a chill water flow of 50%, the AHU capacity will be around 80%. So to get the 50% capacity from the AHU, around 30% of the total chilled water will flow through the AHU and the remaining 70% will bypass. So the net temperature in the chill water return will be lower than the 50 degree Fahrenheit. But to simplify our study, we assume that at 50% of chill water flow, we will get the AHU capacity of 50%. Let us have an example of a building having 6 floors, and each floor is served by an AHU having a capacity of 10 ton refrigeration, a delta T of 12 degree Fahrenheit, and inlet temperature of 44 degree Fahrenheit. Each AHU needs 200 GPM to work for 100% capacity. So the total GPM in the circuit will be 6 into 200 equal to 1200 GPM. So at full load condition, this 1200 GPM will flow through the pump, then chiller, and the whole chill water GPM will pass through the AHU. None of this chill water flow will bypass from the AHU. At part load condition, let us assume our building at floor 6 need 50% of total cooling capacity. So the three-way valve will restrict the 50% of the chill water to flow from the AHU, and it will send directly to the return line 50% of chill water at the same temperature that is coming from the chiller. It means 100 GPM of chill water at 44 degree Fahrenheit will be directly transferred to the return line. When we go to the floor 5, this floor is closed, it is not working, so no need air conditioning there. So total chill water for this floor, that is 200 GPM at 44 degree Fahrenheit, will pass to the return line. When we go to floor 4, here we need 80% cooling capacity. So the three-way valve will send 80% of chill water to the AHU, and this water will enter to the AHU at 44 degree Fahrenheit and it will come out from the AHU at 56 degree Fahrenheit and will pass to the return line. But the remaining 20% will pass to the return line at the same temperature that is coming from the chiller, 44 degree Fahrenheit. In the same way, this level 3 and level 2 and level 1, if we need 50% cooling capacity, so the 50% of chill water will pass through the AHU and coming out at 56 degree Fahrenheit, then go to the return line. But while the remaining 50% will pass to the return line directly at the same temperature that is coming from the chiller. So we have seen in constant flow primary chill water system, even at part load condition, we must maintain a constant flow of chill water throughout the network. And to keep this constant chill water flow throughout the system, we must run continuously the constant speed pump, and it will cause the wastage of power even at part load condition. As we have selected the chiller at fixed outlet temperature, in our case it is 44 degree Fahrenheit, and at part load condition, assuming at 50% of the total building cooling capacity, the three-way valve will allow the 50% of the total chill water to bypass to the chill water return line at the same temperature that is coming from the chiller, 44 degree Fahrenheit, and 50% of the total chill water will pass through the AHU and it will come out from the AHU at 56 degree Fahrenheit. So in the return line there will be two water that will mix, 600 GPM at 44 degree Fahrenheit that will bypass to the return line, and 600 GPM at 56 degree Fahrenheit that will pass through the AHU and will come to the return line. When these two chill water will mix, it will generate a volume of 1200 GPM at 50 degree Fahrenheit. So in this case, the supply temperature of the chiller will be 44 degree Fahrenheit and the suction temperature of the chiller will be 50 degree Fahrenheit and the delta T will be 6 degree Fahrenheit only. As we know, the chiller efficiency is directly proportional to the delta T, so it will reduce the efficiency of the chiller, and this phenomenon is called delta T syndrome. Low delta T syndrome, in other words, we can define as the lower chill water return temperature reduces the operating temperature differential across the chiller, as the supply water temperature is fixed to a set point. So this phenomenon is termed as low delta T syndrome in HVAC industries. So now we can summarize our study for constant flow primary chill water system. At full load condition is more economical than any other system, but we have only for a limited time full load condition, and when the system is running continuously, then we came to the part load condition, and at part load condition we have wastage of power and we are having the low efficiency of chiller. So it will increase the operation cost of the system, but as it has fewer control and fewer equipment, so the initial cost is low in this system, and this system is more suitable for a small central chill water system. But when we go for medium range and larger chill water system, we need some more advanced chill water system that we'll study in next lecture. That is primary secondary chill water system, in which the primary loop uses the constant flow chill water pump, and the secondary loop we have another pump that is controlled by the VFD. So we have variable flow chill water pump in the secondary system, and in primary system we have constant flow chill water system. We will study it in next lecture. Thank you very much.